let me say that it's a great pleasure to have a David Wallace-like pattern in the universal wave function back in London again. So thanks so much for being here, David, and I look forward to the talk.
Thank you. So the title of the talk is a reference to a very interesting and provocative and wide-ranging paper from Doreen and Adam from a few years ago, the Higgs mechanism and superconductivity, a case study of formal analogies. It's a very interesting, provocative, wide-ranging paper that I disagree with on substantial aspects of its non-historical content. And part of the intention of the present talk is to cash out where I want to disagree with Doreen and Adam, but I hope the talk is also a vehicle to explore some broader points in quantum field theory, in effective field theories, in finite temperature field theory, and hopefully it will be useful as a broader point there for some points of discussion. I should say in advance, I'm going to cover quite a lot of physics and I'm going to go quite fast. I'm going to leave approximately 162 conceptual and technical points unmentioned, and I look forward to them being explored in the question session. Okay, so what do Doreen and Adam say in their paper? And as I said, their paper is substantially historical. It's very much an exercise in integrated HPS, and I think their historical exploration looks extremely plausible and extremely informative to me. I'm engaging in a flatly non-historical engagement in where we are in contemporary theoretical physics. But here's Doreen and Adam's position as I understand it. So, as far as superconductivity is concerned, they cash out superconductivity as being caught by two theoretical models. The Landau-Ginzburg model, which is this phenomenological model involving a complex wave function, and the BCS model, a dynamical model involving the formation of a condensate of electron Cooper pairs, and the Landau-Ginzburg model being derivable from the BCS model in certain situations. On the Higgs boson side, the Higgs electroweak side of the story, they primarily have in mind the Glashow-Weinberg-Salam model of electroweak symmetry breaking, but in common with most of the literature, and I'll follow them on this, they mostly actually explore the simpler abelian Higgs model, where instead of considering the spontaneous breaking of SU2 cross U1 symmetry down to U1 symmetry, we just consider the spontaneous breaking of U1 symmetry down to nothing. And instead of generating masses for some, but not all, of the various vector bosons in the GWS model, we generate a mass for the single vector boson in the U1 Higgs model. So that's the set of theories they're considering, and that's the set of theories I want to make contact with. And what they do is look at these theories and ask what are the analogies or lack of analogies between these theories. And the thesis they're interested in, which I want to challenge, is the idea that the analogies between the spontaneous symmetry breaking models and the the superconductivity models and the electroweak symmetry breaking models are purely formal. They're at the level of the mathematics of the theory, but they don't entitle us to any inferences of common physical goings on, even more so common causal goings on, common physics level explanations of what's happening. And there's a sort of rich set of questions as to what it would be for an analogy to be more than purely formal, but to actually be physical or material. And getting too deep into that question gets you into some very general philosophy of science questions about structural realism, about the nature of explanation. But internal to their paper, internal to this talk, we can largely bypass that because the sort of core, again as I read it, of Doreen and Adam's argument here is the analogies between the superconductivity case and the Higgs case can't be more than formal, because even as formal analogies, they're highly partial. And so I won't go through in detail. They consider the degree to which there's an analogy between the Ginzburg-Landau model and the Higgs model, and they say, well, this looks, if there's any analogy, this is clearly where it's going to be, but it's still pretty partial. In particular, the Higgs model has no temperature parameter, Ginzburg-Landau one does, that they say more. They look at the analogies between the BCS model and the Higgs model, and they say these analogies are thin at best. And here's a sort of summary of what I take to be the core disanalogies that I'm going to engage with. So the BCS model also contains temperature. Landau-Ginzburg model contains temperature. The WS and Higgs models don't. The Landau-Ginzburg model is defined in three-dimensional space, GWS Higgs is defined in four-dimensional space-time, and symmetry breaking is a causal process on the superconductivity side. It occurs as I cool the system below its phase transition temperature. I've said critical, that perhaps begs the question as to whether the superconductivity transition is continuous, but the phase transition temperature anyway. There isn't sort of causal interpretation of that kind available in the GWS Higgs situation.
Did you mean physical properties?
No, I think I mean these are formal disanalogies because I don't even have a formal modelling of the process of temperature of spontaneous symmetry restoration in the Higgs side, and therefore there can't be a causal version. But you'll like the slides I'm clear on. That's fine. And the part of their conclusions, as I said, it's a very rich paper, but this is the part of the conclusion I want to engage with, is at most there's a weak formal analogy between the BCS model and the electroweak models. And there is a stronger formal analogy between Landau-Ginzburg and GWS Higgs, but it's purely formal, and it's only partial at that, and precisely because it's only partial, it can't be more than purely formal. And corollary of all of this, they want to say it's unmotivated to look for a dynamical account of electroweak symmetry breaking that stands to the GWS Higgs model as the BCS theory stands to the Landau-Ginzburg model. Which is to say, the Landau-Ginzburg model of superconductivity is a phenomenological model. It describes the superconductor at a level that doesn't need to engage with its microconstituents. And the BCS model gives us a significantly more microphysical account as to what leads to symmetry breaking, and in a certain sense underpins the Landau-Ginzburg model. And they want to say there isn't a motivation for looking for anything that analogously underpins anything we have in electroweak symmetry breaking. And they're writing this in the mid-teens after the empirical discovery of the Higgs boson and after the experimental situation has cleared up quite a lot. But they want to say that, except insofar as physicists are just allowed to speculate on whatever they like and take inspiration wherever they like, there wasn't any kind of pressure to look for instance, Technicolor or other condensate type stories as to where electroweak symmetry breaking came from. There was no reason to want to go beyond what we already had. Okay, so here's the alternative I want to defend here. I want to say there's a physical phenomenon, the phenomenon of spontaneous symmetry breaking. It happens in quantum field theoretic systems. It's a phenomenon that's temperature dependent, it goes away at sufficiently high temperatures. And there are substantive physical consequences of systems that follow purely from the fact of spontaneous symmetry breaking, and from the particular question of what was the symmetry that was broken and what was it broken down to. And those are independent of the details of why and how symmetry is spontaneously broken. But there always is an underlying physical explanation as to why symmetry is broken, and that explanation is logically distinguishable from the bare fact of spontaneous symmetry breaking. And there's no, or to caveat a little, not any major difference between how all this plays out in condensed matter physics, quantum field theory systems, and in high energy physics, quantum field theory systems. As a special case of that, and I'll explore this a bit more in a moment, in the case of the electroweak sector, there's a whole bunch of the phenomenology of the electroweak sector that is explained simply by the pure fact of spontaneous symmetry breaking from SU2 cross U1 down to U1, and then there's a further substantive question about why that symmetry is broken, which is answered in a particular way by the scalar Higgs boson, that didn't have to be answered that way in order to give rise to the general phenomenology of the electroweak sector. Okay, so I want to start off by, I want to do that, by the way, just by basically doing a sort of systematic run-through of how spontaneous symmetry breaking works at zero temperature and then again at finite temperature. So to do that, I want to put up a few sort of baseline assumptions I'm going to make about quantum field theory. This picks up on things that have come up in the discussion so far. So here's the first thing I want to say. So this is a quote from the general abstract of this conference. Quantum field theory is the theory that combines the special theory of relativity and quantum mechanics. So the first thing I want to say is that's not what I mean by quantum field theory. What I mean by quantum field theory is a quantum field theory is an effective theory that describes quantum systems that are effectively continuous on the appropriate scale. So I'm using the term quantum field theory to be completely neutral between the kind of theory I might use to study a metal bar on length scales long compared to the interatomic separation, and the kind of theory I might want to use to study the electromagnetic field or another particle physics situation. I want to say those systems differ in a number of respects, but the respects are about the specifics of the dynamics. So for instance, the space-time symmetry group of the metal bar is the Newtonian group rather than the Poincare group. That means we can get less symmetry-related data out of the analysis. But fundamentally what we have is a quantum mechanical continuum on the scales we're studying it, and we're going to use the methods of field theory to study it. Okay, I'm going to assume, and again this has come up a lot, that the quantum field theories are made mathematically well behaved by a short distance cutoff. The physical details of that are fictitious. They don't affect the large scale physics. So maybe we've got reason to think physically the theory is cut off, probably we don't. In some cases, like metal bars, like the electroweak sector, we have concrete physical evidence of that cutoff scale, like arguably in gravity as well. Maybe in some places we don't have that evidence. But in any case, the cutoff we're imposing is a fictitious cutoff that's used to manage our framework and make it mathematically well behaved. We don't care about the details of the cutoff because we know, insofar as we're wrong about the short distance physics, we can absorb our ignorance into renormalization calculations. This speaks a little bit to some of the issues that came up in Mike's talk. And I'm also going to assume, and this came up a bit in the Q&A after Adam's talk, that the actual systems we're modeling in QFT, whether particle physics systems or condensed matter systems, are finitely large. And so the infinite limit is a modeling idealization, an important modeling idealization, but not to be taken as directly representation. So for instance, we absolutely are going to want to use inequivalent representations at various points in our modeling systems, but we should think about those as different implementations of the infinite limit. I don't take that to be in any disagreement with anything that Adam was saying in the previous talk. Okay, so that's a starting point. That's QFT in general. Oh, and yeah, sorry, add this as well. Particles are localized excitations of field states. They're not, particles aren't part of my fundamental ontology. I get a particle by hitting the system with some kind of excitation and seeing what flies out. And in that sense, I'm using particle as neutral between, say, the, quote, quasi-particles of condensed matter physics, the dressed particles of condensed matter physics, the compound hadrons, the quote elementary leptons that show up below electroweak symmetry breaking scale, and whatever other things you feel like. All of these are challenging, of course, but there's only so much I can do in 45 minutes. Chris, what time did I actually start? I'll assume nominally I was 5 minutes past the time, if that sounds about right. So 10, so I probably had about 15 minutes?
Yeah, about 15 minutes.
Okay, great, thanks. Okay, so let me talk for a bit about quantum field theory at zero temperature. I mean, Adam's already done some very helpful exploration of these, but I just want to get the framework I want to assume on the table. So, zero temperature QFT, vacuum sector QFT, is interested in local excitations, i.e. particles, of the ground state, which in high energy physics we tend to call the vacuum, but all we mean by that is the lowest energy state of the Hamiltonian. In condensed matter physics I might have a background chemical potential, and then I mean something like the lowest energy state of the Hamiltonian at fixed chemical potential, but in any case, hold that fixed as a background assumption. So I have the ground state, I can excite it locally, I can explore what happens. And the physical content of those excitations is encoded in things like this: expectation values of field operators and n-fold product of field operators. These field operators, for convenience, are just single scalars. They don't contain spin or internal degree of freedom labels. In general, they would so contain. Those things exhaustively characterize the state, the instantaneous state and the dynamics of the state. That's not meant to be a metaphysical claim. That's meant to be a mathematical claim about the way the theory works. Effectively, if you know the expectation values of all of the operators, including the Heisenberg operators, all the operators at different times, that exhausts what you can get out of the state dynamics. In axiomatic quantum field theory, that turns into a rigorous result in the context of the Weidmann reconstruction, but it's extremely easy to make it plausible just for physical systems in general. To be clear, what I mean by physical content, the physical content of what you get when you do finite excitations of the vacuum is captured in these expectation values. In Adam's terms, the particular separable sector of the theory that involves finite excitation of the vacuum is described in Hilbert space terms by things of this kind. And normally it suffices to consider time-ordered versions of these where I list the time indices in decreasing order. And it's helpful to stop a little bit and remind ourselves how they encode physical content. Standard QFT tells us the time-ordered two-point functions encode the particle spectrum, whether that's quasi-particles of solid-state physics or various more kind of quote elementary unquote particles in various high-energy physics contexts. Either way, if I want to know what the particles are, look at the two-point function, explore its spectrum. The time-ordered endpoint functions for n greater than 2 determine the scattering theory, or perhaps to be a bit more careful in light of some of the things Adam said, they determine the multi-excitation interactions, which in the zero temperature case I can take to the limit of past and future time infinity and get out of this matrix. And in the condensed matter physics context, it helps to think these are the things that determine the transport coefficients. So if I want to know the conductivity of the system, I get that from studying the endpoint functions for n greater than 2. That's where all the physical content of the theory is living. Particle spectrum and interactions with particles. And just to clarify again, this is true in the condensed matter case as well. It's perfectly legit in condensed matter physics to ask, okay, how does my condensed matter system behave at zero temperature, or at a temperature so low I can approximate zero temperature? So I want to know, for a metal bar, how it conducts at zero temperature. This is the kind of machinery I can use. If I want to know what the speed of sound is in a crystal at zero temperature, this is the kind of machinery I want to use. Okay, so that's the general QFT setup. And I wanted to introduce a little bit of formalism that's useful if you wanted to calculate any of these things. I'm not going to take you too far through calculations because A, this is a philosophy seminar, and B, it's already after 4 o'clock in the fifth talk. So I won't force you through the gory details, but it's helpful to know a little bit about what we're doing structurally. So there is an enormously helpful object you can define in a regularized quantum field theory. Don't heaven help you if you want to do this rigorously in an algebraic framework, called the effective action. And the effective action is a function, I should say functional really, of the classical field. And you can think about it as a quantum version of the ordinary action. Here's a non-perturbative definition of it. Doesn't matter what that definition is. Here's a convenient way of describing it perturbatively. You can think about the effective action as a sum where the first term is the ordinary classical action. I need to renormalize parameters to make this true, but bracket that for the moment. The ordinary classical action plus a bunch of quantum corrections. And in fact, explicitly, if you want to calculate the effective action, you can write it as the sum of all of the one-particle irreducible vacuum diagrams in the quantum field theory, but that's not the definition. This is a non-perturbatively definable mathematical object, calculatable as a sum of classical action plus quantum corrections. Why do I care about it? Well, it pretty much encodes all of the vacuum sector of the theory. If I know the effective action, I can work out all of the interesting stuff happening in the vacuum sector. How do I do that? Well, firstly, if I extremize it, and I'm finessing some boundary condition issues, if I ask what are the minima of the effective action, well, the value of the classical, of the argument of the effective action that minimizes the effective action is the vacuum expectation value of the field. Again, doing it all for a scalar field, it generalizes at the cost of notational annoyance to n-component fields of various kinds. So if I want to know what the vacuum expectation value is, and anticipating a little, that's going to be pretty useful in thinking about spontaneous symmetry breaking. The first thing I do is I work out where the extrema are of the effective action. Normally we assume, and I'm going to assume here, that the ground state is going to be isotropic and homogeneous, so that the vacuum expectation value is not going to vary by spatial location. And in that case, I could simplify this down by just saying, well, what's the effective action worked out for a constant field? That just gives me a function of the constant value of the constant field. And that thing is called the effective potential. It's a special case of the effective action restricted to constant fields. And so if I externalize the effective potential, I get out the value of the vacuum expectation. And then the higher derivatives of the effective action evaluated at the extremum, those tell me the endpoint functions. So they're all, they tell me a little indirectly. They tell me things called the one-partially reducible endpoint functions, which are components that can be glued together to get the full endpoint functions, and are actually more physically transparent than the full endpoint functions. So if I differentiate the effective action twice and evaluate on the extremum, I get out the two-point function that tells me the partial spectrum. If I differentiate it successively more times and evaluate it at the extremum, I'll get out the various coefficients of scattering. So this is a very powerful and useful mathematical tool. It's overkill outside the symmetry breaking sector generally, but for symmetry breaking, it's an extremely useful way to get at the physical content of the theory. And particularly the thing I want to get at, this is a fully quantum object. Generally speaking, when people talk about spontaneous symmetry breaking, particularly in the philosophy literature, we tend to do it classically. But it's important to ask what's a fully quantum description of what's going on. That's particularly going to matter for symmetry restoration. Okay, so with that in hand, let's say what we mean by symmetry breaking. And I'm going to mostly talk, to avoid a profusion of technical troubles, about what symmetry breaking means for global symmetries, and I'm going to hand wave much more in the direction of local symmetries. Of those 167 technical points I'm glossing over, at least 82 of them come up in the move from global to local symmetry. So what do I mean by global spontaneous symmetry breaking? Well, general quantum field theoretic account is spontaneous breaking of a global symmetry in the vacuum sector means there's a vacuum expectation value of some fields that's not invariant under the action of the global symmetry. So if I've got some scalar field, and for symmetry reasons it kind of has to be scalar, if I've got some scalar field and I ask what's its expectation value in the vacuum, and I get out 0, well, that field, at least with respect to that field's expectation value, symmetry is broken. If I get out some number that's non-zero and that the symmetry transforms, well, now I've got spontaneous symmetry breaking. If my overall theory has U1 global symmetry, for instance, and I got a complex scalar field, and I ask what's the expectation value of that complex scalar field in the vacuum, and I get out a number that's not 0, I've got spontaneous symmetry breaking. The effective action gives me a direct way of calculating that. Because the effective potential is extremized by the vacuum expectation value, if I work out the effective potential, and I see that the minima of the effective potential are not invariant under the action of the symmetry, now I know the symmetry is spontaneously broken. And let's talk how you work that out. So you can usefully take that effective potential and write it down as a sum of 3 terms. The first of them is just the classical potential energy of the constant field. You just pull that straight out of the classical Lagrangian. It's renormalized, but otherwise it's just a classical object. Then there's the 0-point energy of the free quantum field theory you get by excitations around a particular choice of vacuum. And then there's some interaction terms that we nearly always hope are 0. So those terms you can think of as being the first of those is the effective is just the piece coming from the classical Lagrangian. The second of those is the first quantum correction, which is, if you like, a free field correction, just created by free field 0-point excitation around around whatever field value you're evaluating at, and then subsequent interactions are picked up by these higher terms and normally discovered. So now we've got a framework where you can see that quantum corrections can start messing with whether symmetry breaking occurs at all. So naively, when you write down symmetry breaking for a field theory, you write down a classical Lagrangian, you observe that the Lagrangian's potential is not symmetry invariant, and you say symmetry breaking happens, and then you imagine quantizing around the 0 point. But to do a more systematic quantum process, you want to be doing 2 things. You want to be saying, okay, how much energy is there in the 0 point fluctuations around a given minimum, and then that's the thing you want to minimize. So the quantum corrections, they could change the vacuum expectation value of a classically spontaneously broken symmetry. In principle, they could even restore the symmetry, or it could be that the symmetry is classically unbroken and it's quantum fluctuations, quantum corrections that break the symmetry. Doesn't matter as far as the effective action framework is concerned. We have a machinery that tells us whether symmetry is spontaneously broken. And if it is spontaneously broken, we can look at the physical consequences. I mean, to pause a moment, if the symmetry is not spontaneously broken, there's a clear physical consequence, which is that particles will turn up in multiples. If my theory has a U1 unbroken symmetry, for instance, it's got antimatter. If my theory has a SU2 unbroken symmetry, it's got two species of particle with an internal degree of freedom linked between them. If I've got unbroken SU3, I've got something like quarks. If the symmetry is broken, I don't have that signature of the symmetry in the particle spectrum, but I have a different signature, sorry. I have the existence of Goldstone bosons, which are zero mass particles that show up in the poles of the 2 point function. Remember that if I work out the 2 point function around the minimum, it tells me the particle spectrum. If the minimum is non-unique, if it breaks, it spontaneously breaks symmetry, it follows that the excitations will include zero mass excitations. And you can think of those as being the ones which in the limit just change what the a particular choice of symmetry breaking vacuum was. That is a very general consequence of global spontaneous symmetry breaking. It doesn't depend at all on the model. And it's not just that Goldstone bosons have zero mass, they have a very specific distinctive interaction structure. Various interaction terms that you might naively think you could write down for a zero mass scalar boson aren't allowable because they break the underlying symmetry. In particular, what that means is the interaction terms for a Goldstone boson have to be derivative terms. They can't depend on the strength of the Goldstone boson field, just on how rapidly it changes. And that reflects the fact that in the limit, an unchanging Goldstone boson field just moves the symmetry breaking point, so it doesn't change the energy. So the tell for Goldstone bosons is zero mass particles with this additional interesting interaction structure. And conversely, suppose I have a theory that spontaneously breaks some symmetry, but it's too damn complicated to calculate in this theory. Well, that might not matter at low enough energies, because Goldstone bosons have zero mass, and hopefully all of the other excitations have some finite mass. And so at low enough energies, I can integrate out all those other excitations, or if you prefer to do your field theory bottom up, I can just build a field theory out of my Goldstone boson excitations and match it. And either way, now I've got a theory just described in terms of Goldstone bosons. And that can be an effective field theory that can describe my sufficiently low energy regime. And conversely, if I find a regime described that way, that's evidence that what I have here is an effective field theory description from some spontaneously broken global symmetry at some high energy. Pause to notice I've said nothing here about relativity or anything like this. All of this is completely neutral as to whether my continuum quantum field theory is describing a solid state system or a relativistic high energy system. A couple of quick examples. So in condensed matter physics, the translation invariance is spontaneously broken, and by the atomic lattice ultimately, and that gives rise to phonons. And the mere fact it's spontaneously broken is enough to tell me the elementary facts about the low energy phonons. I don't care whether the lattice is hexagonal or cubic or something totally inhomogeneous. It just needs to spontaneously break the symmetry, and at low enough energies where the wavelength of the phonons is very long compared to whatever's going on in the substructure, the phonons will just act like generic Goldstone bosons. In quantum chromodynamics, there are no exact spontaneously broken global symmetries in high energy physics, but chiral SU2 symmetry, where I rotate left-handed quarks one way and right-handed quarks the other way, is a symmetry of the QCD part of the standard model, so it's quite close to being an exact symmetry. It's just broken by electroweak effects. And so approximately, that approximate symmetry is then spontaneously broken. And that gives rise to pions, which are low mass particles with a very distinctive excitation structure. And I can do an effective field theory description of QCD just in terms of pions, and I can rely there on the fact that the interaction structure of the pions is what I get out of the Goldstone boson. You had to carry on a little bit of carefulness to recognize this is an approximate symmetry that's spontaneously broken, but you can handle that with just a little bit of care in the calculations. Okay, but superconductivity and Higgs mechanism involves spontaneously breaking a local symmetry. There's a whole bunch of questions as to exactly what that could mean, which I'm largely going to finesse and ignore. I can say some things about them in the questions. At the formal technical level, we can just use the same effective action formalism to explore the spontaneous breaking of the local gauge symmetry. As a very minimal nod to people who have worked on some of this and have some concerns, it might help to say, I think that the cleanest way to think about this is I'm gauge fixing the theory, and then what's being broken is the residual global U1 symmetry of the gauge fix theory. But I can talk more about that in the discussion. In any case, I'm going to use the same trick. I'm going to take the effective action. I'm going to ask whether the effective action is extremized by something that breaks the symmetry or doesn't break the symmetry. And if I find that the effective action is extremized at a level at which the some of the fields have non-zero values, then I've got spontaneous symmetry breaking. And the main difference that happens here is that instead of getting the Goldstone bosons that come out as spontaneously breaking a global symmetry, I get massive vector bosons. So in an unbroken symmetry gauge theory, there are massless gauge bosons that are vector bosons that are the quantum carriers of the long-range gauge force that correspond to the quanta of the electromagnetic or gauge connection. They're massless, that's an expression of gauge invariance. They pick up a mass in the broken symmetry phase. That's again general. It's not quite as general as the Goldstone boson case. There's no known theorem to the effect that I will always get massive vector bosons in a theory of this kind. But there are results to the effect that if I have gauge bosons that are weakly coupled to other stuff, which could be as strongly coupled in other ways as it feels like, then I'll get massive vector bosons. So, in particular, the fact that I get massive vector bosons is not dependent on some specific model of how the local symmetry is broken. It's a consequence just of the local symmetry being broken, provided my coupling constants between the gauge theory and everything else are sufficient. I mean, roughly at the level at which I could do a perturbative expansion and keep the first couple of terms. And again, we can write down an effective field theory for that. So these are not massless particles, but depending on the situation, they may or they may not be lower energy than other things going on. And I can certainly say I can write down effective field theory for all the stuff that has the energy of the massive vector bosons or less than that. And I don't need to worry about stuff at higher energies than that. And the dynamical structure of that theory is determined to a significant degree by the way vector bosons work in a spontaneously broken theory. So I sort of have an analogue here, I hand waving a little bit, but I have an analogue here of the idea that in the Goldstone case, I know there are massless scalar fields present, and I also know something about the interaction structure of those massless scalar fields. So here I know there are massive vector bosons present, and I also know something about the interaction structure of those massive vector bosons. Here are some examples of that mechanism playing out. In condensed matter physics, superconductivity at or close to absolute zero is a consequence of, spontaneous breaking of local U1. Or, if you like, of spontaneous breaking of residual asymptotic global U1. It's a different way of saying the same thing. In high energy physics, the electroweak spectre is the spontaneous breaking of local SU2 cross U1 down to U1. And in both cases, I get out massive bosons of the appropriate symmetry broken type. So in the electromagnetic case, I've broken U1, so I get out a massive photon. In the high energy physics case, I've broken SU2 cross U1 down to U1, so I've still got one massless boson, but I've got three massive bosons. And again, in both cases, the core properties here are just coming out from the fact that I'm doing effective field theory under the assumption of spontaneous symmetry breaking of the local symmetry plus this caveat about weak interactions. I haven't assumed anything about the particular model of how the symmetry is broken. I'm just relying on the fact that it is broken and that the electroweak interactions, that the gauge interaction is not so strong as to invalidate the assumptions going into that derivation. There are some subtleties there about how this works in the high energy physics case because, which I won't come back to this time, because in the high energy physics case, then a different thing we want the spontaneous symmetry breaking to do is to give masses to the quarks and leptons, and that's a subtler matter. But insofar as what we're talking about is the bosonic sector of what's going on, it's just coming in a model-independent way. Okay, so that was all at zero temperature, and that's just a general description in terms of neutral as to what the symmetry is, and neutral as to what the space-time symmetry group is, and neutral as to what the chemical potential is, of what happens when local or global symmetries are spontaneously broken in zero temperature field theory. Okay, what about at finite temperature? So in some ways I'm just going to reprise what Adam said in a very lightning statement of what finite temperature field theory is. But just as in the vacuum sector, that aka vacuum is wrong, that's left from the previous slide, sorry, aka not the vacuum. Just as a zero temperature QFT was about finite excitation, localized excitations of the ground state, so finite temperature QFT is about localized excitations of a thermal state. And the physical content is again sitting in the endpoint functions. It's sitting in the trace of the thermal state with rho of x, the trace of the thermal state with rho of x, rho of y, etc. The imaginary time sum over histories object that Adam constructed is the concrete way you generally calculate these things. But the objects themselves are defined just straightforwardly in the normal quantum mechanical expectation value way. And for what it's worth, these objects, as defined here, they don't contain imaginary time. These are ordinary space-time objects. And again, they're going to encode physical content in the sense of what's the particle spectrum, what are the particle interactions like. For the reasons Adam gave, they won't literally encode S-matrix elements, but they'll encode finite time interactions, and they'll encode transport properties. And all of that is temperature dependent, notice, because there's a beta in these things. So you'll get out temperature dependent interactions, temperature dependent masses of particles, temperature dependent what have you. But again, all of this is neutral as the case. And Adam characterized finite temperature QFT as something that happens at fantastically high temperatures, because Adam had high energy physics QFT in mind specifically. But I mean neutral here. I'm including high energy physics QFT, where if the temperature is less than a gigakelvin, we might as well approximate it to zero. But it also works fine for condensed matter systems where 100 Kelvin might well, or even 10 Kelvin, or even millikelvin in some cases might be high enough that I can't approximate temperature to zero. All works calculationally the same at this level of abstraction. Claim it's all physically the same at this level of abstraction. In each case, I've just got a quantum system, it's thermally excited, it's assumed to be at equilibrium, I'm exploring the structure of excitations around that. And I can carry on doing effective field theory at finite temperatures. And so at low but non-zero temperatures, I can carry on doing my phonon field theory, or my Higgs boson, or equivalent vector, sorry, not Higgs boson, my vector boson quantum vector field theory. But at sufficiently high temperatures, that stops being reliable. And specifically, oh, I'm sorry, my title here is wrong. Pause on my thought for a moment. My title's in there. So I can do effective field theory there. Yeah, but hold that thought. How do I do it? I want to define an effective action for my finite temperature quantum field theory, just as I define an effective action for my zero temperature quantum field theory. And I can do that just fine. Again, I won't force you through the technical details. It's again non-perturbatively the Legendre transform of a finite temperature partition function. And it works just the same way as in the vacuum sector. So particularly if I want to minimize the effective action at a finite temperature, or assuming spatial isotropy, if I want to minimize the effective potential at a finite temperature, that'll tell me whether the symmetry is still spontaneously broken at finite temperatures. So it's the same machine Calculation is different, but the machinery is the same. And again, the particle structure around that will look the same. And again, if you talk about how we calculate that in the analogous way to what we saw previously, I can now decompose the effective potential into 4 terms. The first of them is, again, the potential energy of the constant field. That's coming out of the classical dynamics. It's normalized. That's temperature independent. And notice that if you only see that term, it will be opaque to you that the symmetry could ever be spontaneously restored, because you're only seeing the symmetry break at the level of the classical Lagrangian, and that's just fixed. It just has the same structure, even if the system is super hot. That is the 0-point energy of the free quantum field theory I build from the excitations. Again, that's independent of temperature. But now I also have a thermal bath of quanta of those excitations. The hotter the system is, the more quanta will be present in the calculation. To what extent you can think of this physically, we could debate, but just as a way of visualizing the calculation, you've got the classical term plus the 0-point energy, plus this thermal energy calculated the way we usually calculate it, and then again plus interaction terms that could depend on temperature, but which we normally set aside. But the point about all of this is now we have temperature dependence in the effective potential, and now we have the possibility of symmetry restoration. Because we have the possibility that as the system gets hotter, the thermal energy term can lower the energy of the unbroken value and make it eventually lower energy than symmetry breaking values. And depending how that goes, we can have either a continuous or a first order phase transition. So this is the quantum mechanics of how symmetry restoration happens in a finite temperature quantum field theory. Again, neutrally as to whether that finite temperature theory is condensed matter or high energy. Okay, so to come back to the thing I said prematurely briefly about the effective field theory, at 0 temperature or low temperature, I can just continue doing my field theory in terms of phonons or the Higgs machinery. That breaks down close to a phase transition, in either the Goldstone or the Higgs case. And the reason for that, it's easier to visualize in the global case, is because the Goldstone mode needs to go over to being part of an unbroken symmetry mode above the critical temperature. So think about a continuous phase transition to make this cleaner. Continuous phase transition doesn't involve a discontinuous change in the theory, so I can't suddenly change the number of degrees of freedom I've got in the theory when I go over from the broken to the unbroken phase. So I need to have some continuous transition where the the Goldstone boson degree of freedom goes over to being one of the degrees of freedom of some multiple of particles whose transformations reflect the unbroken symmetry. The only way that's going to be able to happen is if the unbroken particles also, if I have other particle states that have 0 mass at the transition, and so very low mass in the vicinity of the transition. So I've got a bunch of fields around with very low mass. So it's not safe to do an effective field theory only with the Goldstone mode. I need the other stuff in play as well. So I need an effective field theory with more low mass degrees of freedom in place. This, from a QFT perspective, from the EFT perspective if you like, is where the Landau-Ginzburg equations are coming in. They're effective field theories in the order parameter applicable around the critical temperature. And often we want to take an approximation of those equations that's time independent, because we don't care about the quantum fluctuations around there in Adams terms, because we're approximating temperature is high enough that beta goes to 0, so only a four-dimensional path integral becomes a 3-dimensional path integral, and so often we'll write down a time-dependent Landau-Ginzburg equation that's just on space. But again, I think you can helpfully, and again, neutrally between high-energy physics and condensed matter physics, think about the Landau-Ginzburg equations as these effective field theory equations in the vicinity of the critical temperature. It's a place where our previous effective field theories are not as effective, so to speak. Okay, so all of that I've been saying is phenomenological. It tells you how to study what's going on in a quantum field theory if it has a spontaneously broken symmetry. But we still might want to ask, how is it broken? What's the underlying physics when we step out of the effective field theory description according to which the symmetry is broken? And here you can identify 2 possibilities. This isn't necessarily exhaustive. One possibility is that the classical action breaks the symmetry. a fundamental scalar field, where fundamental means relative to my lower level theory, breaks the symmetry. So in condensed matter physics, superfluid helium-4 has this character. Helium-4 is already a boson, it's represented by a bosonic field. That boson becomes a Bose-Einstein condensate at low temperatures. The condensate breaks global U1 symmetry. I get out Goldstone bosons that lead to superfluidity. The Higgs field of the standard model does this as well. In the standard model, I just have a fundamental scalar field. The classical action of the fundamental scalar field breaks the symmetry. It's not restored at 0 temperature by quantum corrections, so the symmetry breaks. Alternative mechanisms, strong quantum effects break the symmetry. Things that don't show up classically, some kind of strong interaction dynamics that mean it's entirely the kind of quantum correction terms in the effective action that break the symmetry. So the BCS mechanism in superconductivity has this form. At low temperatures, electrons form Cooper pairs. The Cooper pairs are bosons. The bosons can then condense. The condensate breaks local U1 symmetry. I didn't put it on the slide, but superfluid helium-3 has this character. Helium-3 is a fermion, but at sufficiently low temperatures, I get a Cooper pair type phenomenon where the helium atoms form pairs, and the pairs are now bosons, and and then again can form a condensate and can lead to superfluidity at a rather lower temperature. In quantum chromodynamics, we saw that the effective field theory of pions tells us that chiral SU2 symmetry is spontaneously broken. What breaks it? As far as we can tell, what breaks it is the formation of a quark condensate below the lambda QCD temperature that Alex mentioned. If Technicolor had been the correct theory of electroweak symmetry breaking, which we're now confident it's not, then that would be a similar mechanism again, the formation of a condensate of techniquarks. It's an empirical matter which of those things breaks the symmetry. You're not going to be able to discover that simply by the general symmetry breaking phenomenology. That just happens as a bare consequence of it. You need to look to the underlying physics to understand what breaks the symmetry. You need to actually look at the energies above which, or the temperatures above which, the symmetry is broken. Okay, so that was a whirlwind tour through how, as I understand it, and there's a lot of physics here, much of which I'm not expert in, so I'm very happy to have kind of corrections or suggestions, but that's the whirlwind tour. Here are the conclusions I want to draw from that. So firstly, and if you like, my case for this is simply that I gave this whole talk neutrally as to what kind of field theories I was talking about. We can and we do study high energy quantum field theory at finite temperature just the same way we study condensed matter purity at finite temperature. There's no fundamental pulling aside here of the two subjects. In both cases, we've just got a hot system and we want to study it. If we do that, symmetry breaking is causal just the same way in high energy physics as in condensed matter physics. I could only study high energy physics at 0 temperature, but I might choose not to, and if I choose not to, I can calculate the effective action, I can find a phase transition. I could choose to study superconductors at 0 temperature. If you look at Abrikosov's book on condensed matter physics, you'll find the first half chapter of his chapter on superconductivity is superconductors at T equals 0. You could just do that. But it's fun to work at finite temperature, and again, in condensed matter, you can see the phase transition at finite temperature. The general phenomenology of electroweak physics and of superconductivity, asterisk the lepton masses, and asterisk a thing called custodial symmetry that I don't have time to talk about, are consequences of local symmetry breaking. They're largely, and that's where the asterisk is, independent of the mechanism for the symmetry breaking. And once I know that that's the case, I can ask what the mechanism is. The GWS model and the BCS model are both mechanisms for symmetry breaking. It's an empirical matter that, as it happens, the mechanism for electroweak symmetry breaking turned out to be a fundamental scalar field and not technical. So to just go back to the analogy case, I want to say the Landau-Ginzburg model is analogous to our high energy physics Landau-Ginzburg model. Not directly to the Higgs boson. It may have formal analogies of the Higgs field, which may have been historically relevantly coming up with it, but at the anachronistic level of the current theory, the Landau-Ginzburg model is a condensed matter, high, close to critical temperature effective field theory. Its analogy in the Higgs sector is just that same object. The actual GWS model is analogous to the BCS model, not in the sense that they have particular features in common, but both of them are underlying mechanisms for how spontaneous symmetry breaking happened. It was an important and urgent question in particle physics once we developed strong evidence that electroweak symmetry is spontaneously broken, to ask what the mechanism was by which it was broken. The first theory we came up with turns out also to be the theory we now think is correct, but it didn't need to work that way. And I think I'll stop there. Thank you.
Dorian.
You want to go first, Adam, or should I? Okay. So thank you, David. We've talked about this a lot, and I always emerge from conversations thinking, okay, you agree with the historical thesis of the paper.
Could you get your mic?
Oh, sorry about that. Yeah. So David and I have talked about this a lot, obviously, and I always emerge from our conversations thinking, okay, you agree with the historical thesis of the paper. And as you said, it is really an integrated HPS paper. And so it's hard, and so there is a philosophical thesis there, but it kind of historically motivated. When I explain what that means in a moment. But so part of the paper is also gesturing towards how the next step would be to think about finite temperature field theory, and then I think there's probably another disagreement between us about whether that's a different theory and what you would mean by saying it would be a different theory. But let me first just say everybody should go and read this fabulous paper, but I'll just explain what the thesis is and in historical terms, and also what the philosophical thesis is. So the historical thesis is that formal analogies were what led to the construction of the Higgs model originally. So David gave a bit of a sketch at the beginning. The idea is that the formal analogies were to the Landau-Ginzburg model. But what was really important to us in looking at that case study was thinking about what the state of physics was at that point. And this actually connects to some of the talks that we heard this morning about thinking about how historical questions arise in physics. But what the problem was Goldstone's theorem in 1961 made it seem as if there was to be spontaneous symmetry breaking in particle physics, you should be finding these zero mass particles, which they should have found already, and there weren't any. Right?
Well, there were some, but in the wrong sector.
Well, right, but they didn't. They weren't the right ones that they thought that they should be finding. Right? So, so that's part of it. But essentially, there's a situation in physics in which they had a general theory, and this ties into Adam's talk. What was unclear was how exactly you would construct models of it that would connect to the phenomenology that people were finding. Right? So the role of the formal analogies was to allow the particle physicists at the time to take the BCS model and the Ginzburg-Landau model for superconductivity, which was a model that had actually been constructed, and to use that as a starting point for thinking about, or to construct by analogy, the Higgs model. Obviously, they didn't have effective field theories, as we know, came much farther down the line. We talked about that today. They didn't have finite temperature field theory. They didn't have any of those ways of thinking about things.
So which year did they not have finite temperature field theory? Just to clarify.
In 1960.
Okay, cool.
Yeah. Okay. So that's the historical kind of puzzle that the paper is about. And so what comes out of this as the philosophical thesis is that if you're interested in questions about what kinds of methods can be used to construct new models or discover new physics by constructing new models, this case and others show that in some cases what you need is a formal analogy, right? In some cases what you need is to follow the mathematics from one domain of physics, which you don't think is physically related to the domain of physics to which your target system is a part of. And so that's the crux of the paper. So the connection to history there is, this is kind of to put it crudely, context of discovery thesis, right? That like, if you are in this position, we're in a much better position in physics now, as David has made clear in his talk, but if you're in this context where you have this new theory and you're unsure how to construct models with it, in some cases what you need is hints about what you can infer mathematically from the general theory you have by way of model construction. So that's the point that Adam was making. While I think it's very nice that you can see, actually I see formal analogies happening all over the place in David's talk, but I think we're probably disagree with that at a more substantial level. But it's nice that you can see that this is just the beginning of a longer research trajectory, obviously, that gets you to a different understanding of what's going on. I'm happy you talked, so that's one point. I'm gonna make another second point, which is, I'm happy you brought up the effective action formalism, because that actually originated by Iono Lacinio, introduced it in the early 60s, because it was useful for thinking about the spontaneous symmetry breaking case, and he was one of the people who was working on it then. So, do we have a board or something, or?
I don't think so, unfortunately.
Anyway, so maybe I'll just say this and we can talk about it in more detail later because it's taking up too much time. But so here's one way of thinking about what goes on here. You put up a bunch of examples of quantum field theories. Quantum statistical mechanics, right, also uses the effective you can use the effective action formalism to have generators for the correlation functions in quantum statistical mechanics. And so then what you get there is the kind of thing that we're pointing out, that what you have is you have the partition function, and so what you have is energy densities, Hamiltonians, and then you have Lagrangians in the field theory case. So that's another way of seeing the kind of connection that Adam and I were drawing in that paper, and also maybe a nice way of seeing how the early work connects to the work you're talking about, right? Because really what needs to be figured out later on is how to move from a quantum statistical mechanical kind of model. Then you have this relativistic quantum field theory model, which is, you could think of it later on as being at zero temperature, but doesn't have a temperature at that time. And then you want to somehow give a thermal treatment of the particle physics model, right? So then that puts you into this kind of framework where you can maybe see the difference in the effective actions, and that might be a good way of understanding how the sequence of developments happened.
Okay, so I'm mostly happy with that. I mean, let me flag just for concreteness, so a concrete point where I think you make a non-historical conclusion that I want to disagree with, and a concrete point where there's a historical normative conclusion I want to disagree with. So the non-historical conclusion is, I think I do directly want to disagree, is you want to say in that paper that we'll have to go beyond the standard model and consider rivals to the standard model if we want to understand spontaneous symmetry breaking in the electroweak case as a causal process in the way we do in the superconductivity case. And there I want to say, I don't think it makes any more sense to say that finite temperature electroweak theory is a different theory than it does to say that finite temperature superconductivity theory is a different theory. The historical normative thing is that I think you want to argue that the Technicolor was not motivated in its own terms, and I think I want to say that I think in the 90s and 2000s, where I think everything I was saying was understood really pretty well, it was still wide open what broke electroweak symmetry. It was totally reasonable to suppose that it wasn't the Higgs framework. The Higgs model was a particular underlying model for the general phenomenology. It was one of a plethora of different models you constructed. I mean, by the late 2000s, Let2's online, and it's getting very hard to avoid a fundamental scalar. And Technicolor, for instance, is in a lot of trouble. A lot of other models are in a lot of trouble, but theory space is large. It really matters a lot that it was eventually pinned down. And I think it made a lot of sense in the 90s and 2000s to be asking, like, what is the mechanism? And you see this in things that physicists were saying in the run-up to the LHC coming online. People were saying, we'll understand the electroweak sector, we might find the Higgs boson, we might not, we think we probably will, but we might not, and we hope we don't. Very few people, I think, were saying that we won't find the mechanism of electroweak symmetry breaking. That was taken as confirmed by the 80s, but it didn't remotely have to be a scalar boson.
Adam can answer that question.
Well, it's a good segue because so I think just in this back and forth, I'm willing, as you probably could infer from my talk, I'm willing to concede that we shouldn't think of those as different theories. And insofar as, to be fair, I also haven't gone back to this paper super recently. Insofar as we do, I'm not speaking for Doreen, but insofar as we do make that conclusion, I'm willing at least to concede that. I was actually, the question I was going to ask was about this conclusion about Technicolor, because again, you've probably read this, making this talk, you've probably read the paper more closely, more recently than I have, but I don't remember ever making that sort of claim. I think the point that I would want to make is that we, not that it was unmotivated, but that, like, it was, in the context of discovery, you have a partial analogy. It makes a lot of sense to try to make that analogy much more complete. It turned out that it wasn't like, it just turned out that wasn't the case. And I almost want to say that, I completely agree that I think it's quite well motivated.
So I talked to David at dinner last night, and then I reread the paper last night after dinner. So I think there's a confusion about the terminology dynamical here, right? So this is a paper about the analogies that were used, and then the point is in the paper that I think we were trying to make was a point about, like, once you have the analogies between the Landau-Ginzburg model and phenomenological model and the Higgs model, then one sort of thing you can try to do is, and you should in most cases, if you have formal analogies, try to find the physics that's underlying them, because that can be a hint to physics, and sometimes it is and sometimes it's not, so you might as well try, right? So the last section of that paper is supposed to be like an analysis of people who are trying to get closer to the BCS model and construct analogies. So I think dynamical and mechanism in that sense is, we were thinking of in terms of like underlying like dynamical mechanism, causal mechanism, in the sense of that you would find it in the, and not in this sense, right? So I think that it's fine with me to call that a mechanism once you have the later understanding of what's going on. I think there's probably, it's not criticizing that program in general, but like the way of motivating it from thinking about how to complete the set of analogies, right? Because analogical reasoning, one of the great things about it is there's a kind of consistency constraint, and so the analogies that were being used kind of violate a consistency constraint. So you could come up with another set of analogies, but then they wouldn't be motivated by the first set of analogies you have. So. Okay,
sure. But then the point I want to make is that the Landau-Ginzburg to Higgs formal analogy is just misleading. It really matters that it's not that there might have been a mechanism we couldn't find one, it's that there was a mechanism. It turns out to be in a fundamental scalar field. Even if there wasn't a fundamental scalar field, physics sufficiently close to the critical temperature would have been described by a Landau-Ginzburg effect, just because it's an effective field theory. And that relates a little bit to the Anderson, the Golyabov stuff you talked about in the paper. There was an open question created by the discovery of electroweak symmetry breaking and the Higgs mechanism, for which the Higgs boson was just one mechanical. I think it's a really good and rich paper, and I don't particularly want to pay gotcha as to exactly what's said where. There's a positive thesis that I think is worth saying, that it's worth understanding, and people who are better at the history of this than I am, I think it's a good project in the 80s, 90s, and 2000s, just how this developed, but there's a clear project of understanding the mechanism of electroweak symmetry breaking, and a huge disappointment, actually, it's something as boring as the Higgs mechanism, as the Higgs scalar boson.
So I just want to say one last thing, which is, yes, but like thinking about what the context of discovery question is, it's how exactly do you get from analogies to hypotheses? And so I think that was the problematic part. So the general project of trying to find some sort of underlying explanation for spontaneous symmetry breaking. It was an open question, and then that motivated good research. But how you use analogies to come up with precise hypotheses was more the question.
Okay, so I want to open it up to people who haven't reread Adam Doherty's paper.
Yeah, sorry, this is very inside baseball.
I did want to ask one thing. I mean, it suggests that there's a historical line of work that you haven't actually undertaken, but this is years ago that I looked at these discussions of why the Higgs mechanism, just as the scalar field, was unsatisfying. But I think there's a more general question, which is, so the structural features of the EFTs are really determined just by the symmetry properties. And so the other mechanisms that people were looking for, like technicolor and so on, could you say a little bit more about what they would have added? Or maybe this is
Sure.
something you've looked into.
Yeah, well, it's not. I mean, it's a question of what they'd have added to. I mean, you can ask what the Higgs boson added. What does the Higgs boson add to the electroweak symmetry breaking framework? Well, one thing the Higgs boson specifically does is it gives us a model to give masses to quarks and leptons. That's quite hard to do in other frameworks. That was always a reason to take the scalar theory quite seriously. We can carve a couple of scalar boson to the fermions. We can't give the fermions elementary mass because it breaks parallel symmetry. That was always fitting in technicolor. It also gives us the angle result that relates the ratio of the W and Z masses to the relative interaction terms. That doesn't require the Higgs boson specifically, but it requires slightly more than just electroweak symmetry breaking. It requires what's called a custodial symmetry, where in the absence of the gauge connection, the global symmetry group is a bit bigger than just SU2 cross Q1. So if you take away the gauge bit of the electroweak sector, you find there's actually an SU2 cross SU2 symmetry for the SO4, if you like, for the Higgs boson. I can just rotate it freely in that space. You also get that in technicolor. So custodial symmetry was recognized very early as a requirement there. Beyond that, what does Higgs get you? Well, it gets you a specific prediction that we will find a rather narrow energy peak at a certain spectrum, a certain energy scale in the once you can actually probe the symmetry breaking regime. If technicolor had been true, you'd end up getting a much messier, broader peak because the bosonic excitation would be very composite. You'd expect to get a bunch of other stuff. There were like as many mechanisms you could think of for breaking electroweak symmetry. None of them. This is the thing about the glory and the tragedy of effective field theory is that it largely finesses away the details of quantum physics, so you can't edge them. So all of these various different models just made different kind of dynamical predictions as to what would show up once we could probe that regime. NEP2 got within a hop, skip, and a jump of probing that regime. I think a lot of stuff was off the table even before the Higgs, but the LHC was turned on. That's the name of it. All manner of different kind of physics there. And in a sense, one of the reasons particle physics is in such a confusion at the moment is that there were very good theoretical reasons to think if there was a scalar field, then it would presage an energy scale at which the theory failed at scales not much higher than that. So hopefully your quote fundamental scalar boson was embedded in some deeper theory where there was a supersymmetric section or some deeper composite structure of higher energies. Notwithstanding the fact that I think there's a really good theoretical argument, they turn out to have false conclusions. The energy spectrum from the Higgs boson up to about 10 TeV appears to be a desert. This is depressing and puzzling, but that's another story.
Yes, Emily.
Yeah, thank you. So in another one of Doreen's paper, I think I remember, sorry, correct me if this is wrong, but there was an argument to the effect that the analogy between renormalization and condensed matter and QFT is also purely formal, and again because the transformation is causal in condensed matter and not in QFT. So I just wondered, could you sort of make a similar move in that case and go to finite temperature QFT and see the transformation looking more causal, or would that not work in the same way?
I mean, the short answer you need to ask Doreen. I guess a broader comment here is, so I didn't really explore this formal versus physical versus causal. So there's a deeper philosophy of science question here. I'm relaxed about the fact that physics describes the world structurally through mathematics, and that if system 1 is described in such mathematical way and system 2 is described by the same mathematics, and maybe if you like with the same spatial temporal features of the mathematics, I've got physical commonalities between what's going on. I mean, I didn't explicitly use the terminology of multiple realization up in the title, but I hope the idea is relatively clear here. You've got the same phenomenon being realized in different microphysics. But you could have a different philosophy of science. You could want something a bit more traditional realist. You could want something a bit more sort of causally fundamentalist. Various lines of that kind might lead you to having a perfect formal analogy, and yet want to say the analogy is purely formal. I think in Doreen and Adam's work on the normalization group, then the argument more rests on the idea that once we understand the physical content of these things, we might recognize the analogies as merely formal, rather than having the richer causal structure. Inside this discussion, it sort of gets preempted because Doreen and Adam's argument is that it's a most formal because it's only partially formal. I mean, there's no analog of temperature, there's no analog of time, there's no analog of symmetry breakers and ample process, these kind of things.
James.
Yeah, thanks, David. This is a slightly lazy kind of...
Could you get closer to your mic?
Yeah, sorry. I'm trying to position it the way. This is a slightly lazy kind of I haven't looked into this, maybe you have kind of question.
Okay.
It's not particularly related to the discussion we've had so far, really. I was curious because you mentioned the approximate spontaneous symmetry breaking of chiral symmetry in QCD. I guess I was just wondering if you have any thoughts about this, given that I guess most of the philosophical literature about spontaneous symmetry breaking has really focused on the case of exact symmetry.
Yeah.
Well, in general, the philosophy of physics literature is focused on exact symmetry, and there's been kind of a neglect maybe of approximate symmetry more generally. But yeah, so I was just wondering, given that in that case you're not going to have these kind of features that philosophers have really focused on, like for instance, multiple vacuum or equilibrium states which are mapped into each other by associated with the equivalent representations and so on. Have you looked into that as a case of kind of potentially deflating some of that focus in the existing philosophical literature on spontaneous symmetry?
I mean, not hugely. I mean, so a couple of quick thoughts there. I mean, one of them, I think if you look at the sort of HPSC literature on this, particularly the earlier part of it, I think it's true that people missed the Goldstone boson step of this in the QCD sector. The way it sometimes gets told is something like particle physicists thought maybe spontaneous symmetry breaking was relevant to the electroweak sector, but it led to Goldstone bosons. They didn't see any Goldstone bosons, so they gave up until somebody pointed out the Higgs mechanism. I think my understanding of this is more what actually happened is they spotted the pions were light and could be Goldstone bosons, and so the attention of the community, and high G physicists are very kind of, they're like bosons rather than fermions, they'll all collect around the minimum. Everyone moved over to trying these ideas in QCD, and so there was this period in, I think, the 60s where that was what people were excited about. It was applying all this stuff to the pion and developing SSB accounts here. And I don't think I've seen a bit more recent things recognise the pion factor, but I don't think I've seen a good HPSC history of that, and it seems to be low-hanging fruit. It's not the kind of work I do, but on the more substantive piece, I think the way you want to think about this is it's like a system that's both spontaneously and explicitly broken. So if you have, if you imagine I've got a ferromagnet in a weak but not quite zero magnetic field, well then of course when symmetry is spontaneously breaking, it breaks in the direction of the magnetic field. And so a bunch of the conceptual puzzles that come up kind of go away. So if you've worked on this stuff in a different context, I mean, there were discussions about whether, in the case of an exact symmetry, how I should be thinking about maybe a fictitious or internally imposed field, and whether that's the right way to think about how the symmetry is, how the problem is resolved, or whether it's the sort of decoherent based framework I like. In this case, it's definitely the externally imposed thing. It's not even externally imposed, it's imposed by explicit terms that we can neglect to first order but not to second. So I think if you think about the electric piece there, it's just the weak perturbation, which forces the system to collapse into the electromagnetically preferred ground state.
So I think I need to trigger a phase transition into the discussion. So sorry for the two of you who didn't get a chance to ask your questions, but you maybe can bring them up in the discussion. So let's thank David.